Hey there, Kim 20s. I just wanted to talk to you a little bit about feedback from the bonding assessment this week. I know not all of you have completed it, but that's okay. I'm just noticing some errors that a lot of students are making. And so I just want to clarify some concepts, make sure there's not a misconception or a misunderstanding. So, one of the ones is when you look at the bonding continuum, you have to understand that you can have a molecule. And when I say molecule, I mean it's a molecular compound, right? It's a nonmetal and a nonmetal. But it can act like or it can behave like an ionic compound based on the continuum, based on if it has a very large electronegativity difference or not. So here's my example to you. I actually have two examples. Hydrogen fluoride molecule. Now I know hydrogen is on the left side of the periodic table, but it does act as, generally, it acts as a non-metal. And so looking at the electronegativity differences between hydrogen and fluorine, 2.2 to 4.0. So then we look at our bonding continuum and we see that it actually falls within this range. When we do that calculation, it is 1.8, which is in the ionic range. So even though it's a molecular compound, it behaves like, it acts like an ionic compound. PF, as in PF3, is going to do the same thing, right? So when you look up P, phosphorus, it has 2.2 for its electronegativity, fluorine 4.0, and you find the difference in electronegativity, same, it's 1.8. So that means that even though you have nonmetal and nonmetal, it's acting like an ionic compound, right? It is acting like it could transfer of electrons, even though they are still molecules, right? They're two nonmetals. Okay, so that is one clarification I wanted to make for you. The next one is when you're determining the intermolecular force called a London force, you have to count up the total number of electrons, not the valence electrons. So for example, if you're looking at CO2, again, to find the number of electrons, you use the atomic number. Your atomic number is your number of protons. And so like CO2, here's carbon, that's the number of protons. It's an atom, so it's also the number of electrons. And then here is oxygen. So that's how you do this. You are doing the total number of electrons. So carbon has 6, and from the periodic table, we're looking at CO2, so we have 2 oxygens. 2 times 8 is 16. Add them up and you get 22 electrons. That's your London dispersion or your London forces. We're not doing valence electrons. We were doing that before when we were drawing out our molecules, and that's still important to do when you're drawing your molecules to do your molecular shape. But you do not count valence electrons for London forces. It's total electrons because you're going to get a different value, right? If you're looking at, well, carbon has 4 valence electrons, oxygen has 6, you get a number of 16 electrons. So this is the number that you are going to use to do your diagram, right? When you are doing a structural diagram or a stereochemical diagram, that's the number you use. When you are looking to do the London forces, it's the total number of electrons that you need to use. Okay, so another thing in terms of strength of bonds, intramolecular, inside of a molecule, is much, much stronger than intermolecular, between two molecules. Covalent bonds are stronger than ionic. They're greater than, stronger than. And hydrogen bonds are the strongest intermolecular. They're stronger than dipole-dipole found in polar molecules, and they're stronger than London forces that are found in all molecules because all molecules have electrons. Okay, so another thing to talk about is students were asked to rank how much a boiling point would be, and boiling point is related to intermolecular forces. So for instance, if you have 2 molecules and you're asked to compare boiling points, hydrogen bonds are going to be much, much stronger than dipole-dipole, and those in turn are even stronger than London forces. So even if you have a huge molecule based on the number of electrons in its London forces, if it doesn't have hydrogen bonding, then even if it's massive, it's going to have a lower boiling point. So here's my examples. Wax C25H52, that has 202 electrons. That's a huge molecule. And I'm going to compare it to water with only 10 electrons. Then I look at, does it have dipole-dipole? No. Wax doesn't, right? It is only got a carbon-hydrogen bond in it, electronegativity difference 0.4, makes it fall within the nonpolar range. So it is a nonpolar molecule. It has no hydrogen bonds. It has carbon-hydrogen bonds, but that is not fluorine to hydrogen, nitrogen to hydrogen, or oxygen to hydrogen. This guy, even though it is a massive molecule, is not going to have the higher boiling point. Water is. Why? Even though it's a smaller molecule, look at the other forces, the stronger forces that it has. It has dipole-dipole. It is polar. That is a stronger force than London. So that means it has a higher boiling point. And the strongest force, the hydrogen bond, it has that as well. And as a result, he's going to have the highest boiling point. And you know that he boils at about 100 degrees Celsius. Wax, if you guys have a Sensi at home, you know that you put a little light bulb on and it maybe melts somewhere around 30 degrees Celsius. Okay, so much higher boiling point. Why? Because it has a dipole-dipole, that high electronegativity difference. It is a polar molecule and it has a hydrogen bond. Okay, another little caution for you is please do not mix up Lewis diagrams, structural diagrams, and stereochemical formulas or VSEPR diagrams. Remember, when you're doing Lewis formulas, you're using dots. And structural formulas, you use lines to show the bonds. You do not add in the electrons, right? You do not mix the two of them together. And finally, if you're asked for a stereochemical formula, that's a VSEPR shape. So that means that you have to do those funny arrows, meaning this guy sticks out at you, this guy goes into the paper behind you, right? You have to use those funny bond arrows, okay? And so make sure you're doing that and don't combine the two of them. Don't add dots to structural and lines to Lewis. That is not correct. And one other thing that, again, students were kind of struggling with was hydrogen bonding. This is an unusually strong intermolecular force. It's stronger than dipole-dipole, and it's much, much stronger than London force. The only time you see a hydrogen bond is in 3 cases. If a fluorine and a hydrogen are bonded to one another, an oxygen and a hydrogen are bonded, or a nitrogen and hydrogen. Now that is a covalent bond, right? The fluorine and the hydrogen are sharing electrons. This is a covalent bond. This is a sharing of electrons. This is an intramolecular force. But here's where the intermolecular force comes into play. This is an attraction between, remember, nitrogen is very highly electronegative. It has a high electronegativity. Its value is 3.0. Hydrogen, 2.2. So we have a very strong polar bond there, the electronegativity difference being about 0.8. You can do the math on your own. And so this is a dipole. So basically a hydrogen bond is a special case of a dipole-dipole, but it's very unusually strong. So that means that the electrons are more around the nitrogen atom. It's more negative. And the hydrogen is not very negative. It tends to be more positive. So this attraction between the nitrogen of one atom and a hydrogen of another is this intermolecular force that we know as a hydrogen bond. Okay, and so it is between atoms of fluorine and hydrogen. So when H and F are bonded, O and H, like water molecules, N and H, like when we have ammonia. Okay, so you have to have a covalent bond between H and O, H and F, or H and N. C and H is not a hydrogen bond, right? It is only when it's to one of these very highly electronegative atoms, F, O, or N. Okay, so hopefully that clarifies some things. A lot of people had errors. I just wanted to clarify, make sure you guys are understanding. Okay, sounds awesome. If you have questions, michelle.ledeen@ghsd75.ca. Okay, we'll talk to you later.